So lecture 43 on conservation of energy. Before we get to that, I wanted to just revisit something we did yesterday where we talked about the force of a spring, right? It's equal to the displacement in some spring constant, right? So if we were to graph force versus displacement, right? This would be a line with slope k, right?
Yeah.
And I said that the work was equal to the area under this triangle, right? But let's think about that just for a minute, right? So we can imagine looking at, say, in this first little interval, right? Here, what's the work that's done in this interval, right? And we're going to approximate it as just this little rectangle here, right? So here the force is, you know, kx, where this is x, right? And then to get the work done over a larger displacement, right, we would add up more of these little rectangles, right? So I'll say this is like a delta x, okay? And so this would be k delta x, right? And so I could add up all of these rectangles, right? So to get the work that I did, I add up these rectangles, which are all getting a little bit taller each time, right? So here's another delta x, right? Delta x is always the same. It's this distance right here, right? And so to get the work done from, say, going from here to some distance maybe here, let's just go one more. All right, so I'll create one more little delta x, right? One more little rectangle that I compute, right? So I add up this area, which is k delta x times delta x, plus this area, which is k delta x, right? But now it's kx, I guess, kx, right? So how far I am from the equilibrium point of the spring, right? So this is always increasing. The rectangles are always getting taller, even though the widths are always the same. It's delta x, right? So I'm adding all these little things up, right? If I make these rectangles small enough, such that this little bit that I overcounted by here, see this area here, and this area here, right? And this area here. If I make my delta x small enough, then I'll minimize these little pieces here, and I'll be left with just the area under this curve, right?
Yeah.
Which is a triangle, and so we can easily calculate that, right? Because we know that it's the area of, say, this rectangle, right, which is kx, pi, and the distance here, right, the sum of these little delta x's, which we'll just call x, right? So here's this distance here, right? And it's half of that, right? The area of the rectangle is kx squared, but the area of this triangle in here, right, is 1/2 kx squared, okay?
Okay.
And so we'll when you get to calculus, you'll see a lot of little problems like this, when we add up the areas of rectangles with smaller and smaller widths, and we take the limit as the width of these rectangles approaches 0, right? And this will lead to a concept called integration, which we'll do in calculus. Yeah, so I didn't think I did a good enough job explaining that, so I just wanted to revisit it briefly. Okay?
Okay.
Now on to the topic of today's lecture, which is conservation of energy. And so recall that we said that the potential energy, delta U, was equal to minus the work, and we'll say, conservative work. Okay? Because this only really applies for conservative forces. And we also had the work-energy theorem, right, which said that the work, and I'll just keep the conservative subscript on here, was equal to the change in the kinetic energy, right? This was the work-energy theorem, right?
Yeah.
So if I do work on a system, there's going to be a change in the kinetic energy of the system, okay? If the masses stay the same, then there'll be a change in the velocities, okay?
All right.
If I now substitute in delta U for this, right, I would get minus delta U, because of that minus sign, is equal to delta KE, right?
Yeah.
If I add delta U to both sides, right, I'll be left with delta KE plus delta U equals 0.
All right.
And we call this statement the conservation of mechanical energy, okay?
Okay.
And so that's what we're going to explore in this lecture. Let me just rewrite this up here. Delta KE plus delta U equals 0. And we'll start with a pendulum, right? We haven't really talked about pendulums and the motion of pendulums yet, but you know what they are. If I take a ball and suspend it from the ceiling with a rope,
Yeah.
and then I pull it and let it swing, it's going to oscillate back and forth, right? Now assume there's no loss, there's no friction or air resistance or anything like that, it's just going to swing forever, okay?
Yeah.
And an important result, well, I'm not going to go over that right now, but you get the idea of it swinging, okay? And so at the top of its motion, right, here's the attachment point, here's the string, here's the ball of mass m, right?
Yeah.
And we'll have a little, this is going to be my 0 marker for potential energy, okay? So this is where it'll start, right? It's at rest, I just lifted it up, I'm going to let it go. At some point, right, it's going to be straight down, right? Like this,
Yeah.
right? And it will have a velocity v, right? I'm going to say that this is the velocity v here, okay?
Okay.
And then if I continue to let it go, right, it's going to swing back up, right, on the opposite side. I'm trying to get this looking exactly the same. Right? And we'll be back to this position again, okay? So the potential energy, you will recall, right, if I measure this distance from my 0, so I'll say this is u naught equals 0, right, so that's where I'm measuring from. Here is a delta x, right, that's the height the ball is above this marker. This marker is where it's going to be when it's fully extended, right?
Yeah.
That means that delta u, right, is equal to the mass of the pendulum times the gravitational acceleration times delta x, right? That's its potential energy at this point. What's its kinetic energy at this point, right? Actually, I'm just going to say u equals, okay? Since u naught is 0, we can just say that, right? What's the kinetic energy at this point? Well, that's 1/2 times the mass times the velocity squared, but it's not moving. Its velocity is 0 here, right? So this is 0, so equals 0. So at this point, all the energy is in the potential energy, right?
Yeah.
I release the ball, it swings. Now, right, the delta x is 0 here, right? So I'll write delta x is 0 at this point, right? Which means that the potential energy, mass times g times delta x, this is 0, right? Whereas my kinetic energy, right, is equal to 1/2 mass times the velocity squared. So at this point, all of the energy of the system has been transformed into kinetic energy, you see?
Yeah.
And then it continues to swing back up again. What is it here, right? It swings up till it comes to rest, right? So now its kinetic energy is 0, right? So here V equals 0. I'll write V equals 0 here as well, right?
Yeah.
So at this point, the kinetic energy is 0. Its potential energy is again, right? This distance, if it's all completely lossless, right, is delta x again, right? So it's mg delta x, and its kinetic energy is again 0. Okay? So you can see that the system, as it's oscillating back and forth, it's going from all the energy is in potential energy,
yeah,
to at the point where it's at its lowest in the swing, right? All its energy is in kinetic energy,
yeah,
back to all of its energy is potential energy again. So it's constantly cycling back and forth between potential energy, kinetic energy, potential energy, kinetic energy, right?
Yeah.
In between, if we were looking at a spot in between here, its velocity would be slower, right? Because it's slowing down as it swings back up. So it has a little less kinetic energy than it did at this point here. This is where it'll have its maximum kinetic energy, right? Or its maximum velocity. But it'll have a little bit of potential energy because it'll be some fraction of our delta x, right? Maybe it's half of that, right?
yes,
So we could figure out how much kinetic energy it had if it only had half of that, right? Because those two things are equal. This conservation of energy says that the sum of this plus the potential energy plus the kinetic energy, right, is equal to 0, okay?
okay,
Yes?
yes,
So this is a pendulum system. Let's look at it for a spring, okay? It's going to look very similar. So for a spring, maybe it starts out in a compressed state, okay? And we'll say that the equilibrium distance is here. So we've pushed it in, right, from where equilibrium would be, the spring would be here, and I push it in so it's compressed, okay? And this is, again, an object of mass m, right? So it's not moving at this point. I haven't released it, right? So if all of its energy is in potential energy, right? And so that'll be 1/2 k delta x squared, right? But its velocity is 0, so its kinetic energy at this point is just 1/2 mass times velocity squared, but that's 0 because the velocity is 0, right?
yeah,
And then at some point later, right, the spring will be at, I should have drawn them on top of each other so you could see, but I had 4 of them, right? So here, we'll say that delta x equals 0, right? It's returned to its equilibrium position. It's moving, right? It has some velocity, right, going in this direction. And I can figure out easily how much velocity that was because the potential energy at this point, right, is 1/2 k delta x, squared, but delta x is 0, so the potential energy is 0, which means that all of the energy is now in the kinetic energy. Okay? So whatever this was, right, this would be some value, a number, right? That's what the kinetic energy is equal to at this point. Because all the potential energy got turned into kinetic energy at this point. And then, of course, the spring is going to stretch. I'll try to draw it kind of stretched looking. Right? And now it has, again, a displaced, instead of being compressed by delta x, now it's stretched by delta x, right? So its potential energy, if it's completely lossless, is the same as it was over here. 1/2 k delta x squared. Okay?
Okay.
But its kinetic energy, of course, is 0 because it stopped moving at this point, right? It stretched out to its maximum stretch. So it's oscillating back and forth. And as it does so, it's going from all the energy is potential energy to at the midpoint, all of its energy is kinetic energy, to the stretched point where all the energy is again potential energy, and then it returns. It goes backwards, right?
Yeah.
Oscillating back and forth. Okay?
Okay.
So that again is because of conservation of energy. I could figure out, let's say, this speed was here, if I knew what the spring constant was and how much I compressed it, right?
Yes.
I could calculate what the velocity is at this point quite easily. All right, now let's look at a ramp or an inclined plane. So I'm going to do the diagrams a little bit differently for this one. So here's my incline, okay? And we'll say that this distance here is some height h, right? And I'll put my little ball up here of mass m at the top, and then I'll release it, right? And so at point 1, right, what is the state of the system? Well, its kinetic energy is 0, but its potential energy, right, U, if I measure with, if this is U naught equals 0 here, right?
Yeah.
Its potential energy is m times g times h, right? But its kinetic energy is 0 at this point because the velocity is 0. Now, when it gets to the bottom of the ramp, right, well, this point 2, right, its potential energy now, at 2, is 0 because mg times h, right, is 0. So potential energy is 0. Its kinetic energy, on the other hand, is 1/2 mass times velocity squared. And so if I want to know how fast this ball is going, right, at the bottom of this ramp, I can use conservation of energy to figure that out. So this one I'll do to an actual numerical example. Okay? Let's say that h was equal to 1 meter. Okay?
Okay.
We know that g is 10 meters per second squared, right?
Yes.
So its potential energy in this case would be, and we'll say the mass is 1 kilogram. So m equals 1 kilogram. So we'll have 1 kilogram times 10 meters per second squared times a height of 1 meter, right? This is going to give me 1 times 10 times 1 is 10 joules, okay? So that's its potential energy at position 1, okay? To figure out what its speed is, right, I'll use conservation of energy. And I'll say, well, 10 joules is equal to 1/2 mass times velocity squared, right?
Yes.
So solving for, we know that mass is 1 kilogram, right?
Yeah.
So what does this tell us? This tells us that the velocity squared is equal to 2 times 10, right, which is 20. And that's going to be meters squared per second squared. And now I need to take a square root of that to see what the velocity is, right? So our velocity then would be square root of 20, that's 5 times 4 is 20, so that's going to be 2 square root of 5 meters per second. Okay?
Okay.
Now, the interesting thing is the details between point 1 and point 2 don't really matter, okay? So I could have, instead of having this nice straight ramp down, right, this could have been a kind of bumpy hill, okay? And because of the way we did things, conservation of energy does not care about the details in between, as long as there's no losses. If there's friction or something like that, then we have to worry about it. But if we say that it's a frictionless system, then it doesn't matter if it had to roll down the steep hill, then back up, and then down, and then down, right? It's really just the potential energy plus the kinetic energy at point 1 will be the same as the potential energy plus the kinetic energy at point 2. And since the only thing that differs here is this height h, right?
Yeah.
That's all you need to calculate that. And so you can figure out what the speed of the ball is on this crazy path just by knowing how high the ball was when it started and how high it is when it finishes. Okay?
Okay.
That's interesting, right?
Yes.
Well, to see if you understand that, let me ask you the following. Let's imagine we have a roller coaster. Okay? Looks like this. Okay?
Okay.
And your roller coaster starts off at this point right here. Okay? Which is some distance above our 0. Which I'll draw out at this point here. Right? This is where our potential energy, I'm defining as being equal to 0. So our measurements for displacement will be measured with reference to this line. Right? And so this displacement, this initial displacement is delta x1. This hill here, right, will be a delta x2, which is greater than delta x1, okay?
Okay.
Kind of as I've drawn it, right? It looks like it's taller, so it is, right? I'm stating that it is. My question is, if I release this guy with no initial velocity, mind you, so I start him at rest, and I let him go right here. He's going to roll down the hill, picking up some speed, right?
Yes.
We just calculated before what that speed would be at the bottom of the hill, right?
Yes.
And now he's going to roll back up the hill, right? Is he going to get to the top of this hill?
No.
No, he's not, right? The highest that he could get, right, is this distance here, delta x1, okay?
Okay.
If it's lossless. If it's not lossless, if there's friction and air resistance, then this distance will actually be a little bit less than that, okay?
Okay.
Because energy would be lost to heat and stuff, okay? We'll talk about heat when we get to thermodynamics, but all right. So the answer to this question is no, it will not. Right? The highest that it could get is this point right here, delta x1. And if delta x2 is greater than that, it'll never get over that hill. I'm going to switch gears just a little bit here. I want to talk about work in 2 dimensions. Work in 2 dimensions. Of course, what I say about 2 dimensions will also apply to 3 dimensions or more. Okay, but it's easier to talk about it in 2. So if I have some trajectory that the particle is going through, right? Maybe it's a track, okay? The work, right? If this is the displacement vector, right? Well, let's draw it a little bit big. So if my displacement vector is like this, right? I'm going to call this S. It's a vector, so I put a hat on it, right?
Yeah.
If the force I'm applying is not in the same direction as S, right? Let's say that the force I apply is a little, makes an angle, theta, with the displacement, right?
Yeah.
So it's like you're on a track and I'm pushing at some angle that's makes angle theta with the track itself, right?
Yes.
I'm not putting all the force in the direction of the motion, right? How do we figure out what the work is? Well, it turns out the work, right, will be equal to a dot product. And I think we've talked about dot products before.
Yeah.
It'll be F dot, and I call this S, so I'm going to call this S, okay?
Okay.
Which is, by definition, it's defined as the magnitude of F, right, times the magnitude of the displacement, times the cosine of the angle between them, okay?
Okay.
So if we look at this and we imagine constructing a right triangle out of this, we need to create a perpendicular here, right? Then the magnitude of F, right, times the cosine of theta, right? Well, the cosine of theta is the adjacent side divided by this, right?
Yeah.
And what's happening here, and the way to think about it is, a lot of times we call dot products projections. So you imagine you take this force vector F, right? I guess I should have drawn this to the end of the vector. Like so. That's my right angle, right? I project it onto this axis. And sometimes it's easier to do this accurately if you make the S, you align it. That's not straight. As a horizontal line. So here's my S, right? And then here's my F. And I make this right angle line down like so, right?
Yeah.
And so the projection of F onto S is like the shadow that would be cast if you imagine shining a light from directly above, perpendicular to S, right?
Yeah.
It's the shadow that's cast down here, okay? And so that is the component of the force, right, that's acting in the direction of the motion, okay? And so the work that you get is actually the force projected onto it like that in the direction of motion, okay?
Okay.
So, if you want to optimize it, right,
Yeah.
you'd want to make sure that your force was completely aligned with your displacement. So you're not pushing the car on the track at an angle, you're pushing it straight from behind, right?
All right.
Now I'm going to look at a general diagram. So this will be a Cartesian plane, x and y. These are both distances, okay?
Okay.
And I'm going to start off at some point, and we'll call it, I think in my notes I call it A. Yeah? A. And I'm going to consider another point B, okay? And I want to talk about the work that I do through three paths, okay? So I've got one path that comes along to here. I've got another path which pretty much goes straight to B like that. And another path which comes around like this. And I'll call this path 1, call this path 2, I'll call this path 3, right? Now, conservation of energy, right,
Yeah.
tells us that if I start in some state A, at some position A, and I do work that's conservative work, right? I'm assuming all the work here is conservative.
All
So
right.
conservative forces, it's elastic or it's gravity, right, or electrical. If I do work, I can use that dot product definition to find what the work is along this path, right? So my force would be applied in the direction of the motion around this path, and I add all that up, right?
Yeah.
If I go around, say, through path 1 to B, and then all the way back, maybe down path 3, back to A again, right? That the change in energy, right, will be 0. Okay?
Okay.
That's just another way of saying, you know, conservation of energy.
Okay.
So the work, you know, from A to B back to A, right, is 0. So work. It also says work AB along path 1, right, will be equal to the work from A to B along path 2, which will be equal to the work from A to B along path 3. This is a little bit like what we did with our bumpy roller coaster ride. I said, look, it doesn't really matter. I can just make a straight inclined plane, right?
Yeah.
The details in between don't matter, right? The amount of work that I have to do, right, that I do in moving along that trajectory is the same, regardless of the details in between, okay? So it doesn't matter which path I take, right? The work that I do to get from A to B will be the same, right? As a consequence of that, going back from B to A, right, that'll be the negative of that, and so the sum of the two will be 0. If that was not the case, then you could create, you know, perpetual motion, and you could create perpetual motion machines, okay?
Okay.
Things that, you know, lift a ball and then lower the ball back down again, but now that I'm back at the bottom, I have more energy than I had before. Maybe I've got some potential energy. That's just not possible, okay? If it was, then you could create machines that whose output provides the input for, say, the next cycle of the machine, and that's just not, that's another way, saying that there's no such thing as perpetual motion machine is another way of saying conservation of energy applies.
Okay.
Yeah, so the path doesn't matter, okay?
Okay.
And so the reason that I bring this up is because in the next lesson that we'll have will be on simple machines, okay?
Okay.
And the idea that the work that you put in is equal to the work that you get out, right?
Yeah.
Is the consequence of conservation of energy, okay?
All right.
Now in real machines, of course, the work you get out will be a little bit less than the work you put in because there's always heat generated and stuff like that. And these are these non-conservative forces which don't give back, right, the energy that we put into it, okay?
Okay.
And we'll understand that a little bit better when we talk about thermodynamics. But right, the last thing I'm going to talk about is power. And this is mostly because of, I didn't mean to erase that, but that's fine. Power. Mostly for a homework help. There'll be some homework problems that will deal with power. And so what is power? You've probably heard of it, right?
Yes.
When have you heard of power before?
Powerful people, powerful machines. I
Okay.
assume you're talking about. Oh, I don't know what you're talking about in this case.
Okay, have you ever heard of the term power in, say, relation to, say, car?
Yes. Yes.
How would someone describe a car in terms of how powerful it is? Have you ever heard the term horsepower?
Yes.
Have you ever heard that? That's a nice car you got there. How big is that? How powerful is that engine? Oh, it's a 500 horsepower engine, right? That'd be a pretty powerful engine, okay?
Yeah.
Yeah, so horsepower, power, right? So what is power? Power is the work done divided by the time, okay? So it's a rate of work, so we can write it as work divided by time interval, delta t, okay? And remember that work, right, is force times delta x, right? So I'm going to write this as big P for power,
Yeah.
work divided by the time it takes to do the work, where I replace work with force times displacement, right? And I can rewrite this as force times delta x over delta t, right? Which is velocity, right? And in general, I can write this as a vector quantity, force dot velocity, okay? So I take the dot product of the projection of the force onto the velocity, okay?
Okay.
So for a weightlifter, for example, right? His power, right? His work is mgh, right? The height that he lifts the weight, right? Divided by delta t, right? So I can rewrite this as m times g times, I'm going to call this delta h, right? Maybe delta h, right? Over delta t, okay? So delta h, that's the speed at which he's lifting it, right? He's changing it from a height of 0 to a height of, say, 2 meters, and he's doing that in 1 second, right? That's 2 meters per second. That's pretty quick, right?
Yeah.
So here's the velocity component that we were talking about there, okay? And then that times mass times acceleration, right? So you can think of the difference if he lifts it slowly. If the change in height from going from 0 up to 2 meters takes 10 seconds or something, so it's a real slow lift, right?
Yeah. Yeah.
That doesn't have as much power in it as it would if you did an explosive lift, right?
Yeah.
Okay? Only other thing I was going to mention about power, and this will be useful for the homework, right, is that sometimes, so for example, horsepower. What is 1 horsepower? 1 horsepower, well, I think it's 746 watts. Oh, I completely forgot to mention. A joule per second is a watt, okay?
All right.
He's named after James Watt, I think. Another guy in thermodynamics, okay? So the unit of power is the watt.
All right.
So 1 watt is 1 joule per second, okay?
Okay.
So I guess I could write that up here. 1 watt is equal to 1 joule per second. Well, joule is energy, right? Okay?
Yeah.
So 1 horsepower is equal to 746 watts. Okay? If you walk around the house, take a look at the light bulbs, you'll see that they come in, they're rated by the power that they consume. Okay? You might have a 20-watt bulb. It used to be, like your standard house light was 60 watts. That was the old style light bulb. And a really bright one would be 100 watt. Now they usually give it to you and they say, oh, here's a 60 watt equivalent or a 100 watt equivalent. But it'll really be more like 20 watts because they use LEDs, light emitting diodes, which have much less power consumption. But they produce similar intensities as the old light bulbs, which have a higher power rating, you see?
All right.
That's why they're better, because they require less power, which means you pay less to use them, okay? What else do I have up here? A lot of times energy will be described in terms of power. The most common example is if you pay an electrical bill, right? They quote how much energy you've used in units of kilowatt hours, right? So kilowatt hours, right? So that's a unit of energy because kilowatt is a unit of power, right? And power is work divided by time, and so I have units of power times time. That's energy, you see?
Yeah.
And what is 1 kilowatt hour would be equal to, just check it, 3.6 megajoules, okay? A megajoule is 10 to the 6th joules, okay? Using the SI prefix system, mega, all right?
Yeah.
Another useful thing is 1 gallon of gasoline, it's called gas, is equal to 40 kilowatt hours, which is equal to 144 megajoules. Right? So you'll want to have these conversions to use because in the homework you'll be given some problems. That's about the power consumption in a home, given if you've got some light bulbs, other things, right? And another one will be what's the required horsepower for a car that gets 30 miles per gallon. Okay? So these conversions will be useful in solving those problems.
All right.
And that's all I had to say about that.